Lecture 6. It's a continuation of the topic Data in GIS, Acquisition and Input. In this lecture, we'll be talking about specifically coordinate systems. And coordinate systems as they relate to any data set that we're going to collect. Now, as I said in previous lectures, we need to work with a common coordinate system in our GIS analysis such that we have our data sets being able to be overlaid over each other in order to view the data together, all together. This is the table of contents for lecture 6. We're going to look at what is a map projection, scale, the effect of scales, what is graticule, types of projections, distortion patterns, what determines best procedure in selecting a map projection, what are spheroids and datums, and lastly, some commonly used projections. Now, please note that map projections by itself, a course by itself, because there are so many different map projections out there, as you would see when we start doing the hands-on exercises. In any GIS, there are a lot of map projections already programmed into the software. This lecture is actually geared towards to just giving you an idea or a little taste about how important it is to consider map projections and coordinate systems. Map projections. Within the past millennium, there has been more methods used to map continents and whole hemispheres. Globes are useful because mapping on them entails no distortion in distance, in direction, in shape, in area, and proximity can be measured on a globe. Globes are scale models of the Earth. Now, ideally, if we all can, walk or go out in the field with a map that is represented by a globe where we can make measurements, it will be ideal. However, globes are not practical for us to use. Instead, we are using a piece of paper that, because we're using a 2D piece of paper to represent the 3D, there is some distortion that will be introduced in the map that is being displayed. Some impracticalities of globes. Globes are bulky and are not very functional for mapping detailed features. Now, if I have a globe and I want to be able to see see a building or make measurements of a building on the Earth's surface, a globe would not have that level of detail. Distance and area computations on a globe are more complex because they require spherical trigonometry. And spherical trigonometry, just to give you an idea, a spherical triangle on a sphere does not add up to 180 degrees. So it's a different approach in terms of the concept displayed or concepts of spherical geometry as compared to your basic trigonometry. Because of these impracticalities, projections were developed to transform our spherical coordinates to planar coordinates, which is planar being a 2D environment. Projections are a systematic rendering of the latitude and longitude gradicule and allow the sphere to be transformed to a planar or flat surface. There are an infinite number of projections. As I said in the previous slide, when you start working with the GIS software that's out there, they have a lot of predefined map projections, and the choice of them, which we'll cover later on in this lecture 6, where the criteria we would use to determine which is a suitable map projection. Scale. What is scale? The size of geographic features is typically reduced to enable features to be represented on a map. We cannot plot features from real world to that on a map at a 1-to-1 scale. If that was the case, then we would not have enough paper to represent the entire surface. The amount of reduction is what we call the map scale. Scale of a map is the ratio of the distance on a map to a distance on the earth. So it's a distance on your map to the same distance on the ground. All right, there's a ratio between them. Scale is represented on your map in different forms. There are 4 methods of representing it. Geographers are trained to refer to maps as large or small scale. Example, a 1 into 50,000 is a large scale, while a 1 into 1 million is a small scale. Now, whenever you talk about large and small scale, now it must be known that whenever you use those large and small scale, it has to be with respect to 2 scales. Which one is a large scale relative to the other? Scales are also expressed using words. It can be also expressed as 1 inch equals to 1 mile. Scales can also be a representative fraction, such as 1 to 24,000. Note there is no units attached to it. Scale can also be expressed as a graphic scale, and this is more commonly seen and used. It can, as shown in the diagram there, you have a graphic scale that starts from 0, goes up in 2 kilometers, 4 kilometers, and on the left hand side you have divisions of the 2 kilometers. It is important to know the scale of the map you are working with and to understand the associated resolution and detection levels. Now, if you collected, for example, if you did a GIS application and you collected data at a scale of 1 to 10,000, okay? Now, at that scale, you would very unlikely be able to see or capture the dimensions of buildings. Now, when you develop that application and you present that to a non-GIS person and they are amazed by your application, and then they might come up to you and say, well, can you show me my house? Well, in order to display that data at the household level, it means that you would have had to capture at a scale where you can get the dimensions, and you did not do that. So you could keep on zooming that data set that you collected for 1 into 10,000, and there is no house. So it's very, it can be very misleading to the non-GIS people why they cannot see their house. All right. Determining polygons that have areas smaller than the area of the minimum detectable size feature will help you understand what features can be represented. So in other words, I'm trying to say there is that you need to identify what do I need to show on my GIS. And based upon what I need to show on my GIS, I can choose a suitable scale. For a given data set, you cannot get any better at the scale in which the data set was collected. So if I collected it at 1 to 10,000, I cannot get anything better than 1 into 10,000. Okay. On this slide is an example of what is large scale and what is small scale. Now, in order to, as I said before, to compare large and small scale, it has to be relative to another map. So at least in order to say one map is larger than the other one, it has to be at least two maps we're talking about. So in this case here, you see two maps. 1 into 5,000, when we compare that map with a 1 into 50 million, the 1 into 5,000 is the large scale, and the 1 into 50 million is the small scale. What you see here is 1 into 5,000, we can actually see road networks, we can see blocks and buildings, as opposed to the 1 into 50 million, the most we can see is actually the country boundaries. That's another example of large scale and small scale. Now, this map here is considered small scale when compared to another map that has a large scale information here. Now, this map, it's we are seeing road networks, okay, but we cannot see the buildings. On this map here, we are actually seeing blocks on both sides of the road, so much more detailed information. So this map is our large scale map, as opposed to this one here, it's small scale. Graticule. A graticule is a set of meridians and parallels that represent the locations of lines of longitude and latitude respectively. So graticule is actually a line of longitude and latitude which is used to define locations on the Earth's surface. What is a meridian? A meridian is a line on the Earth formed by the intersection of the plane passing through both poles. So meridians are actually lines of longitude. A parallel is a line on the Earth's surface formed by the intersection of a plane that is normal, which is perpendicular, to a line drawn through both poles. So parallels are, for example, lines of latitudes. This is an example. There are three examples of different maps and different coordinate systems. And also what I want you to note here is that the graticules, the lines of longitude and lines of latitude, they differ. In this case here, in the global representation of all of the countries in the entire world, the graticules in them, the longitude are curved lines which meet at the north and south pole, and the latitudes are parallel but straight lines. In the other example here with Australia, the longitudes are straight lines, but they meet in the southern part, well, South Pole, and they converge to the South Pole and they diverge towards the north, while the lines of latitude are curved. In another example here of South America, the longitudes are straight lines and the latitudes are straight lines. So it makes a big difference what we are talking about in terms of the coordinate system. types of projections. There are three geometric projection surfaces that we use in order to represent features from the Earth's surface. The surfaces are the plane, a cylinder, and a cone. A plane works simply by laying a plane on a piece. It's as if you put a piece of paper on the Earth's surface, on the globe, touching at only one point. And where it touching the Earth's surface at that point, we have zero distortion. As you move away from that point, the distortion of features increases. A cylinder works similar to like you are wrapping a piece of paper around the globe and then projecting the features onto the projecting the features from the Earth, from the globe onto the piece of paper. Then you would unroll the piece of paper, and then there you have it. It's a map. The third surface is your cone. It's work like making a hat or a cone and placing it anywhere on the Earth's surface. Once it's placed on the Earth, on the globe, then you would project the features project the features from the globe onto the piece of paper, which is your cone. And as you move away from the area where the cone is touching the globe, the distortion would increase. This slide shows you the three projection surfaces. We have planar, or some people say planar, conical, and cylindrical. Note in the notes, another name for planar is azimuthal. The spelling is in the lecture notes. You can download it, and when you review it, make sure you know the correct spelling. So there are three projection surfaces, and in the planar, it's orthographic, where we are assuming the light source is at the center of the Earth, and my plane surface is actually assumed to be touching the North Pole. And when we project everything towards that flat surface, this is the output of my map. My point of zero distortion is going to be at that center, which is at the North Pole. And as we move away from the point of tangency, of the point, we move away from that single point, the distortion increases. In a conical projection, we assume again the light source is at the center of the Earth, all three of them. We assume that the surface is a cone, and we project everything outwards. And as we project everything out, so we would open that cone, and this is our final map. Where the cone is touching the Earth's surface, that point of tangency, it's going to be that line of zero distortion. As you move away from that line and away from that line, the distortion is going to increase. This is our cylinder projection surface. We assume that the light source is at the center of the Earth. Put a cylinder over the entire Earth's surface. We assume that, of course. And wherever the cylinder touches the Earth's surface is going to be that line of zero distortion. Everything else is projected outwards. When we open that cylinder, this is going to be the form of our map. We have lines of zero distortion here, which is in this case here, the equator. As we move away, the distortion increases. These are some examples of your planar, or your conical, and your cylindrical. Now, please note here your plane, another name or term referring to your plane surface is azimuthal, as shown in the top left diagram, azimuthal. Here you can see the continents on the Earth's surface using a planar surface or an azimuthal surface where it's actually touching the North Pole, and everything else is projected, every other country is projected onto that plane surface. At the bottom you see a cylindrical projection system, and if you note here is, if you look at the South Pole, it's a big landmass. Note here, this can be very misleading. Okay. On your right, you see a conic projection, and once the land masses are projected from the globe onto the conic surface, it's opened out, and we have the graticules in them as shown in that diagram, but it's actually originated from the dimensions of a cone. Projection characteristics can be classified by also the light source location. This is another variable. So apart from the surfaces that we spoke about in the previous slide, another variations in our projection system is by locating the light source. There are three types. It can be gonomic, stereographic, or orthographic. Gonomic. That is, the light source is located at the center of the globe. This means that any great circle, the shortest distance between 2 points on the globe is a straight line on a gonomic projection. And a gonomic projection is typically used for aviation. So for pilots in them, they would be using gonomic projections because it depicts straight line, shortest distance. Stereographic, light source is located at the point exactly opposite the point of tangency of the projection surface. Orthographic, the light source is from infinity. The following slides are going to show you diagrams of how the variations of light source, gonomic, stereographic, and orthographic. Gonomic, that is, the light source is located at the center of the globe. So there you see the light source is assumed to be at the center of the Earth, and everything else is projected onto that projection surface. Alright, so this is another variation in our map projection. This is another diagram showing more detail of what is done in a gonomic projection, where the light source is assumed to be at the center of the Earth. So there are light sources at this location here, and everything else is projected outwards on a plane surface. And as we move away from that point of zero distortion, the distortion increases. So my point on the Earth's surface is actually it's going to be larger distortion as we move away from that point of zero distortion. Stereographic, the light source is on the extreme side, opposite, exactly opposite to the point of tangency of the projection surface. Zero distortion occurs where the projection surface touches the Earth's surface. Alright, as you move away from that point where it's tangential on the Earth's surface, distortion increases. This is another representation of stereographic projection. We're assuming the light source is on the opposite side of the Earth, and this is our plane surface. We project all the features from the opposite side of the Earth, and your coordinate system will define the location of where these features are. This is the output of my map. If I use a stereographic projection with a plane projection surface, then my line of zero distortion is going to be along this line here, which is our equator in this case, and all the other lines of latitude is going to be curved in the opposite direction depending upon which part of the hemisphere we are mapping. So quite a different representation. It all depends, of course, what is our intended application. An orthographic, it assumes that light source is from infinity. Alright, and this is another variation, and they're quite different, and it all depends upon what type of projection system you are wanting in order to minimize the distortion in terms of data set that you will be collecting. This is another representation, the same example of orthographic projection, assuming that our light source is from infinity and all the features on the Earth's surface is projected onto a plane surface. And this is the end result of my map, where in this case I have in an orthographic projection lines of longitude are curved and lines of latitude are parallel lines. Distortion patterns. Because all projections have distortion, it is important to understand how the geometry of the projection leads to minimal distortion in one location and maximal distortion in others. Now, this is you need to understand that, because if I am interested in a specific study area, I want a projection system where my distortion is going to be minimal. In all of my explanation in this lecture 6, I spoke about the surfaces being tangential, touching the Earth's surface or touching the globe. Now, in the tangent case, distortion is minimal at the point of tangency, and the distortion increases with increasing distance from that point of tangency. Now, another variation in our projection system is that instead of having our surfaces, that is our plane, our cone, and our cylinder, instead of having them touching the globe, we can have it in the form of a secant case, S-E-C-A-N-T, where that is the effect of cutting. Instead of touching, it's actually cutting the Earth's surface or the globe. There is minimal distortion at the line of tangency, and the distortion increases at location towards the center of the map and away from the line of tangency. So if your surfaces, the plane, the cone, and the cylinder actually cut the globe, it's not a point again, but instead it's a line where there is minimal distortion. This holds for your planar and your cylindrical and conical surfaces. This is an example through a diagram of the effect of distortions. Now, if I map an island, a fictitious island, all right, and I use different projections. In this case here, we're using a planar surface or plane, or an azimuth, also called azimuthal, or that particular feature shows up in this shape using a planar surface. Using a cone, the same feature shows up like this, quite different to what it will show up like on a planar surface. And if I use a cylinder, that same feature has a different shape. So it all depends upon what what am I mapping, what is the area, where it is located, and choose the appropriate surface in order to minimize distortion. Along my cylinder surface, this is my line of zero distortion. Along my cone, this is my line of zero distortion. And my plane surface, that point there is my point of zero distortion. I can have a projection using the three surfaces, cylinder, conical, and azimuthal. Instead of touching the Earth's surface, I can have it in a situation where each one of these surfaces actually cuts the Earth's surface. In this case here, it's called secant projections. Alright, so it's going to be a cylindrical secant projection. In this case here, using a cylinder, I have two lines of latitude of zero distortion. In my conical secant projection, I have two lines of zero distortion. In this case here, I have it at this location, or I can have it at this location here where it enters the Earth's surface, assumed to have entered the Earth's surface, and where it comes out the Earth's surface. Two lines of zero distortion. In my azimuthal, I'm going to have, instead of a point of zero distortion, when it's using a secant projection, you have a line instead of a point in the original when it's touching, which is tangential. And when it's in secant, it's actually a line of latitude in this case here of zero distortion. How do you select a projection? There is already a standard projection such as state plane coordinate system for county and city governments, or there is also a UTM used by state government here in the US. All right, so sometimes it's already selected for you in terms of what coordinate systems that I need to use. Then if you use with working for the city government, you will be using city and county. You will be using state plane, which we'll talk about later in a while. And if you're working with state governments, you use UTM, which we'll also talk about in a later while. Factors to consider if a projection system is not already predefined for you. Factors to consider when selecting projection: the latitude of the area, where is it in terms of the on the Earth's surface. How big is that area? The extent of the area. All right. You can assume that if it's a small area that you're working at, let's say about 30 kilometers by 30 kilometers, that's very small relative to the size of the Earth. We can assume that the Earth, for 30 by 30, the Earth is flat. All right. That does not say that you don't define a coordinate system. By all means, you always use coordinate system and map projections in all of your data set. And the other factor you would consider when selecting a projection is the theme of the area. What am I collecting? Am I collecting data, pollution data? Am I collecting land use data? Am I collecting census data? It's very important because if I'm collecting census data, it might be that I don't need to have an accurate dimensions of countries if I'm looking at collecting census data globally, as opposed to if I'm collecting data that a land surveyor is collecting data in terms of property boundaries, different projection systems there. This slide gives a summary of the various projection services and how it is being used to map the entire Earth's surface. Here you see the cylindrical surface being used to map the entire Earth's surface. In this case here, we have certain areas in the tropical and some of the temperate regions, lower temperate regions, being mapped accurately. But as you move away from those areas of minimal distortion, you have the South Pole being mapped as a huge landmass, which is incorrect, and also the North Pole also. Here's another example of the conical, this is your conical projection surface, where the entire Earth's surface is being mapped, and my North Pole is shown more accurately, as opposed to as you move away from the North Pole, the land masses have a different shape, which is, so there are some inaccuracies there. And lastly, this is our planar projection system, where in this case here the South Pole is being mapped accurately, but as you move away from the South Pole, South America is highly disfigured. Another aspect you need to consider is spheroids and datums. The Earth's shape is not a perfect sphere, but bulges slightly at the equator. So the Earth, as it is, you know, yes, Columbus was correct that the Earth is not flat, but it's not a clearly defined sphere. It's actually what we call an ellipsoid. All right. Where there's a semi-major and a semi-minor axis. All right. One example of ellipsoid is your spheroid. Is defined by two radii, an equatorial radius and a polar radius. That's the semi-major and the semi-minor axis, and an eccentricity constant. Now, your spheroids and datums are used in the definitions of your projections in the coordinate system. We use mathematics. We can use mathematics to represent the Earth's surface by way of these coordinate systems. So the coordinate systems, we would use mathematics to come up with these coordinates to locate features on the Earth's surface. Spheroids are used to parameterize a coordinate system called a datum, a set of control points. All right, so this is a little, you would see these terminologies coming up when you start looking more into details of coordinate systems and projection systems. This diagram shows the two surfaces that are used to represent the Earth's surface. One being the ellipsoid or the spheroid. This, as in the lecture notes states, the ellipsoid and the spheroid are surfaces that would represent the Earth's surface using mathematics. So I can use the formulas that we would have to at our availability to define an ellipsoid using semi-major and the semi-minor axis. So the ellipsoid and the spheroid are shown in this diagram in blue, and the red line is what we call the geoid, and that surface is not mathematically defined. It's observed. It's derived by a dense set of observational points that uses a lot of computational methods to come up with a surface that closely represents the Earth's surface, and that surface, the best surface, is what we call a geoid. Land surveyors make use of this in their GPS receivers. Actually, the new GPS receivers make use of the geoid as a reference surface, and it gives you more accurate positioning of points. Now, in the GPS receivers that we have in the market, you can change between the geoid and the ellipsoid. Okay, so I want you to know that a more accurate representation of the Earth is by way of the geoid. Now we're going to look at two commonly used projection systems here in the U.S. One is your Universal Transverse Mercator, UTM, and the other State Plane Coordinate System. UTM, acronym for Universal Transverse Mercator. It extends a flat grid from 80 degrees north to 80 degrees south. There are 60 zones starting at 180 degrees longitude and wrapping around the Earth. Each zone is 6 degrees longitude wide with an additional 0.5 degrees of overlap on each other. UTM, when we refer to lines of longitude and latitude, here in the U.S. is what it's consistent. And the lines of longitude and latitude in another country, let's say in Russia, Europe, is going to be a different coordinate system that they're using. All right, but here in the U.S. they use UTM. And this is an example, a mock-up of a diagram of a UTM zones for the world. All right, if they was to extend the coordinate system to cover the entire surface. State plane coordinate system. It's the other type here in the U.S. we used. It is used for local areas, usually for counties or cities. Each state is divided into a number of zones. Up to 5 zones is allowed. Zones with a greater north-south extent. Now, if your state it's elongated in the north-south direction, then they would use UTM projection. Zones with greater east-west extent, then they would use a Lambert conformal conic projection is used. So state plane coordinate system, there's quite a variation when it compared to your UTM coordinate system. This is an example, a little diagram of the U.S. of the 1983 state plane coordinate system zones. Note, for example, in Florida, there are 3 zones, and there are variations of them in terms of its east-west elongation and its north-south elongation. Now, if we overlay the counties in the background and we have our state plane coordinate system zones, we can see which county falls in which zone. And that's a simple application of how useful GIS is in order to determine where counties are in relation to the zones that they are using. This last slide, we're looking at some examples of commonly used projection systems. And I wanted to show you this to just give you an idea of how much of a distortion in terms of the feature being displayed on the Earth's surface. If I'm drawing a map, preparing a map of the entire Earth's surface, how much of it is that the feature is being distorted by. You see on the top there, geographic, the South Pole is one huge landmass, which is not correct. All right. However, the intent of that map is to show the continents about, not so much the South Pole, but more of the continents where we have a lot of people living. Then there is the Peters projection. There, the South Pole is not as big as in the geographic. And you have Mercator, and you can see the differences. all right, between one projection system and the other. And again, which one of these would you choose? It all depends upon the intended GIS application. This concludes this lecture on data in GIS. I advise you to download a PowerPoint notes page, go over the material, make sure you understand it, and we'll continue with the next lecture.